Very good afternoon to you, ladies and gentlemen. At the outset, may I extend a very warm welcome to all participants on behalf of CII. The webinar initiative of the CII is very well appreciated by our members, and we have organized over 115 online sessions since its launch in 2009. Over 5,000 members have participated, and the feedback from them is quite encouraging. Today's webinar will be on the topic Stainless Steels for Corrosion Prevention by Dr. Kamachi Mudali, Indira Gandhi Centre for Atomic Research. Dr. Kamachi Mudali is Head Reprocessing Research and Development Division, in addition to Head Corrosion Science and Technology Section, Reprocessing Plant Materials, and Head of Technology Transfer Cell at Indira Gandhi Centre for Atomic Research, Kalpakkam. He joined IGCAR in 1984. He has almost 30 years he has spent with the IGCAR. He is a leading materials and corrosion specialist, well known internationally for his contributions in localized corrosion, advanced materials, and coatings and development for severe corrosive environment and surface modification for corrosion protection. Dr. Mudali has published over 150 research papers in journals, about 160 in proceedings, books, and internal reports, and has 2 patents to his credit. He has delivered about 110 invited presentations and chaired several technical sessions in national and international conferences. Dr. Mudali is a professor of the Homi Bhabha National Institute, Bombay, and an adjunct professor of PSG College of Technology, Coimbatore. Besides guiding and coordinating thesis work of engineering graduates and postgraduate students at IGCAR at Kalpakkam, he has visited as scientist at several leading international institutions located world over. Dr. Mudali has been honored with many prestigious awards. He is a member of the editorial board of international journals of corrosion reviews, surface engineering, materials and manufacturing process, and journals Materials, Science and Technology. May I request all participants to make a note that this webinar will be a one-way communication from CII Chennai. The live interactive session would begin after the presentation by Dr. Mudali. You will be able to type the questions at your computer, which will be read by the speaker, and he will take them live and answer them. Participants are requested to type the questions and await the speaker to take on the question and then answer. May I, on behalf of the participants, extend a warm welcome to Dr. Kamachi Mudali and invite him to take over the session. As he is about to take over the session, I would like to tell you that at the end, the entire proceedings recorded will be available at my CII in a couple of days' time, where you will be able to see the presentation and hear the speaker. Thank you, and over to Dr. Mudali. One second.
Good afternoon. Are you able to listen to me? Good afternoon again. I am Kamachi Mudali, Associate Director of Corrosion Science and Technology Group and also Head of Reprocessing Research and Development Division, Indira Gandhi Centre for Atomic Research. I am also teaching in the Homi Bhabha National Institute of Department of Atomic Energy at Kalpakkam. I am very pleased to give this webinar, CII webinar on stainless steels for corrosion prevention. I have given my contact details and the email. If you are not able to get your questions answered in this session, you are most welcome to send me emails and also call me if you want to have more discussions. The topic that I have given to CII was stainless steels for corrosion prevention. I know that only a very special group of people and the special group of industries are dealing with stainless steels more than steels for very specific applications, very strategic applications. And all of us, there is a myth, all of us feel that stainless steels never corrode. Some people think that stainless steel means you can use like anything, it will never undergo any corrosion and can be used safely for many applications. But it is not so. If you look at my outline of the lecture, I am giving it as a popular lecture rather than focusing on any very technical aspect. And if somebody attends this lecture from first point, what are stainless steels, why they are important, to the last point, the summary of that, you will have a broad knowledge about the types of stainless steels, its invention, properties, application, and how they are manufactured, the basic aspects of stainless steels and their classification. Particularly, I will talk about austenitic stainless steels, duplex stainless steels, superaustenitic stainless steels, and the specific problems of corrosion of such stainless steels. Some issues like practical issues like surface finish treatment, weldability, storage and preservation. I felt that in an hour or so now from now, I will be able to satisfy you with all this information. But please remember, each one of these points that I have given can form 1 hour lecture. So I am just trying to condense and give you in a lecture, 1 hour lecture, that you get a wealth of knowledge on stainless steels and their application for industry and their corrosion prevention. When I speak about corrosion, with my vast experience over last 30 years, I did my MTech corrosion at IIT Bombay 1982 to 84, and ever since I have been working on respect of corrosion. It's a natural disease of materials, in a simple way you can say. Wherever there are materials being used and wherever there are environment, be it is underwater, be it is on air, be it is on space, you will have always the problem of corrosion. It's a destructive interaction between the material and the environment. And 90% of the material that are used in the industry today are ferrous materials. We know that it is being extensively used. And rusting, the most common type that anybody will know in the society, is an important corrosion attack that is observed on the iron-based materials in all type of environments. There was an estimation of the cost of corrosion in USA in the year 2002, and they found that about $276 billion are being wasted due to corrosion, and that could have been about 40% of that $276 billion could have been saved if proper corrosion prevention has been attempted. And they also made statistics that about 3 to 4% of the GDP is lost every year due to corrosion by all the countries. If you take 3.5% GDP as the average value, if you look at the GDP of India in December 2011, and if you calculate 3.5% of that, I'll tell you in a mind-boggling number, it's about 3,72,000 crores lose every year in India. Considering that it is only 3.5%, which is estimated for all the industrialized countries. So even if we can save 40% of that, about 75,000 crore can be saved if we adopt some basic corrosion prevention strategies. So it's a very important phenomenon that has to be understood, and that has to be controlled and prevented before it happens. It's an interdisciplinary subject. It involves materials, it involves environment, it also involves some basic sciences. Let us take for an example, if we are using iron as a material that is used in the industry for various applications, and if it is corroding, I can say that iron will simply dissolve to form a ferrous ion. That is, it will release some electron and it forms an ion in an environment. This electron is consumed by reduction reactions, either at another metal surface or within the metal surface here itself. So the metal that is corroding iron is called anode. The electron where it is consumed, the couple, that is called cathode. The metal dissolution releases electron, so metal is oxidized to metal ion, so it is an oxidation reaction. Electron is consumed here, it is getting reduced, so it's a reduction reaction. This is called a cathode. For example, you take any metal, metal will release its electron according to its valency state and become a metal ion in the environment. For example, iron can become Fe2 plus with 2 electrons. Aluminum can become 3 plus, aluminum 3 plus and 3 electrons. These electrons are consumed by cathodic reactions starting from hydrogen evolution, which will happen in any acidic solution, or oxygen reduction in a basic or acidic solution, or metal ion reduction or deposition. So corrosion occurs by metal dissolution at the anode. The electron released thereafter will be consumed at the cathode, which is a reduction or cathodic reaction. And during corrosion, there is a balance. Number of electrons that are produced here are equal to number of electrons consumed. The same way, number of metal atoms that will become metal ion and the reducing pieces here. And if you look carefully here now, there is an anode that is involved, there is a cathode involved, there is a medium, environment conducting medium which is involved, and there is a connecting link between them involved. So these are the 4 important parameters. If I want to stop corrosion, I can mask the anode with some paint or something, or I can make this conducting medium into non-conducting medium, or I can cut this connecting link using a flange or using something gasket in between, or the cathode can be also made very larger area. So we can try to manipulate with the parameters of anode, cathode, conducting medium, connecting link. One can try to see corrosion prevention strategies. The basic question comes in all our mind is that why is that all the metals and alloys would corrode first? The metals are produced from the ores which are available on the Mother Earth. It's not that easy. We get the ore, mine them, extract them, melt them, and mix some metals together. We make alloy also, either as a metal or as an alloy. And these are all made into engineering components by working with them, machining them, and welding them. And we make different types of components, tanks, pipes, flanges, so many things. But during operation and service, corrosion is one of the damaging mechanisms, like fracture, fatigue, scaling. It makes the component to see its end of life, by which the component meets its end of life and it is becoming waste. The economy is lost from where the ore started. The metal goes back into ore when it becomes a waste. The energy that we put in to extract the metal from the ore, to make an alloy, to make a component, and then operate is lost. The economics is lost, and we also generate wastage. This is the natural corrosion cycle of material, because all metals are extracted from the ore, which is a natural stable compound. To take iron, the ore of iron is hematite and magnetate. Nothing, it is iron oxides. from iron oxide, they are practically taking the iron out, somehow killing the oxygen. So the iron metal is always hungry for oxygen to again form the ore that is iron oxide. So it's a natural phenomenon. Corrosion cannot be avoided in surveys. Now our strategy is to how to avoid this corrosion, or how to delay this corrosion, or how we can try to slowly stop the corrosion from happening, so that I have a lot of service life for the component in the service. In this way, I am going to speak now the entire lecture about a class of material, stainless steels. What are stainless steels? A wonderful material that is having unique properties which made them to be used in various industries for corrosion resistant applications. They are basically a generic term for a family of corrosion resistant alloy steels containing 10.5% or more chromium. They are made as pumps, they are made as pipes, they are made into sheets, they are made into towers, wires, tanks. So many components are made using this family of alloy steels called stainless steels. Who has invented the stainless steel? History says that Harry Berrerly, a British metallurgist working in British Steel, around 1911, has found that chromium above 10% can prevent the erosion and fouling of rifle barrels, which are used frequently in the war, which was having a problem of corrosion and fouling, erosion and fouling. And this is just a story just starting 1911 to 1913. Not only this British metallurgists, there are also other scientists and engineers from other countries who are also finding similarly that chromium, when it is added beyond some level, is providing a kind of non-rusting behavior. That is how today we are celebrating 100 years of stainless steel. There are 150 types of stainless steel, more than 120 types of stainless steel used in the industry, and this is the year that 11 and 12, 1911, that is 2011 and 12, we are celebrating 100 years of stainless steels. However, the word stainless was coined first by Ernest Stuart, a manager at a cutlery company, who described first stainless cutlery knives. Probably this person, the manager of the cutlery company, was involved in supplying the cutlery articles like knives, spoons, and so many other items, which were getting stained after being used for the food. But probably he found one type of steel that was made with a little more chromium was not having any stain formation, so he found the word stainless. That is how the stainless steel started. If you want more details, to look at the ferrous group of alloys, the iron alloys, the alloy steels, and stainless steel, I give a little more information here. All of us know the family of steel, that's iron carbon alloy, as carbon steels, alloy steels, and stainless steels. If you look at the iron alloys, from the meteorite or the prehistoric iron to Delhi iron pillar, which is 1,600 years standing erect without much corrosion at Delhi. And then you have various other iron carbon, phosphorus, sulfur, manganese alloys, then the iron carbon steels. From here, the situation improved to alloy steels, where people started adding chromium, tungsten, and probably they were all manipulating with the chromium to form an alloy steel, which will have better property than the iron alloys. Very surprisingly, you see here Michael Faraday, who also added chromium, and then found that there are no corrosion issues, but he did not declare it, he did not made it public to the society, but he also studied the iron chromium alloys in his investigations. Later you come to the stainless steel group. You can see Haynes, and then Moyer and Strauss, then of course Harry Berrerly, Stuart, and Borchers and Thomas, and Gillett, and Goldsmith. Many people, they started using various combinations of nickel and chromium, and they also found that the minimum percentage of chromium, about 10.5% is required to have this stainless property. This is the early development of stainless steel is like this, but if you look at today, 2000s, and from 1911, lot of developments have happened. Today we have mastered the technology of stainless steel to produce from a normal conventional stainless steel to a high alloyed, highly clean and with tailored properties for various applications. You can see that nickel and austenite structure, low carbon ferritic structure, then duplex stainless steels, understanding more on the physical metallurgy, then welding and other technologies. Then they found this problem of sensitization and intergranular corrosion. Then with respect to the technology for manufacturing using AOD process, cleaner and lower carbon nitrogen containing and submerged welding, continuous casting, vacuum induction welding, electroslag remelting. Then also new varieties like superaustenitic stainless steel, high nitrogen stainless steels, life cycle casting, then highly alloyed stainless steels. And today you have a lot of nanotechnology based, intelligent welding, pattern rolling, tailoring the surface. Many developments are happening. Stainless steel is growing and growing. We have more than 150 types of stainless steels in different classifications. A simple and fundamental point that everybody thinks in the mind is, why is that the stainless steels are stainless? If you look at the formation of a non-rusting thin surface layer providing a stainless nature is the important concept of giving the stainless steel a stainless area. This passive film layer is made of chromium oxide, Cr2O3, and it forms when the chromium content is greater than 10.5% in the steel. This productiveness can be enhanced, the stability of the passive film can be enhanced by adding higher chromium content and also addition of molybdenum, nickel and nitrogen. Look at the picture here. As you see the chromium content is increased, you see the corrosion weight loss. For example, in simple water or outdoor use for atmospheric condition, you see even about 10.5 is enough to give a very low corrosion rate. But if you go to a corrosive environment, as much as you increase, the corrosion rate is coming down and down. People can add up to maybe today commercially up to 30% chromium in stainless steel, forming the superaustenitic stainless steels. What are the benefits from stainless steels? Corrosion resistance, high temperature properties, low temperature properties, hygiene and aesthetic appearance, ease of fabrication, toughness and impact resistance, and cost and life cycle cost. These are some of the best benefits that one can get from stainless steels. If somebody has to tell that where and all stainless steel is used, you can go on, make a list where you will find from domestic to industrial, from underwater to aerospace, and from chemical storage, waste storage, and you can keep on list them. I put a typical pictures of various stainless steel components that are being used. This is a very important point. The most important point I feel that this is one material where life cycle costing is very important. If you look at the life cycle of stainless steels, from the melt, you can fabricate various components, use it in the industry for various applications. Ultimately, it doesn't become a rust and then you are throwing it. It becomes a scrap. The scrap can be remelted. So by secondary melting and improving the quality, you can again go back to use these stainless steels for further application. It's as good as I can say no scrap, 100% it is recyclable. That's the most important economical point. How are they manufactured? The three simple steps I am putting here. The number one step is they are first melted in electric arc furnace. After fixing the charge, the amount of chromium, nickel, carbon and iron, in an electric arc furnace it is melted. You can also use scrap SS directly as a starting material. The melting occurs around 1500 degrees close to the melting point. Then the step 2, this is converted to transferred to a converter where argon oxygen decarborization process is used to decrease the carbon by blowing out with oxygen, and then alloying elements are adjusted in order to match the composition. Then in the third step, it is poured and the molten mass pour the molten mass into a mold, and then you make billet or whatever you want, cast structure, rod structure. And also you can do a continuous casting by rolling them up to 2 meter wide and up to 300 millimeter thick. You can then a special set for hard rolling, and This can be done after slab grading. This is a very simple step. Step 1, make the primary melt. Step 2, you make that should be again treated with an argon oxygen decarborization process to adjust carbon and other alloying elements. Third step is you are making into a wrought product. Now, this is a typical flow sheet that is followed in an industry like Jindal Stainless. You are the pioneers in the stainless steel manufacturing in our country, where the raw material from raw material stage, they go into arc melting, then or backmount converter if the alloying elements like the impurity elements to be controlled precisely. Then they go to ladle refining, then either continuous casting or bloom casting. So you get a slab or bloom or coils by continuous casting, then it is all treated, then it is sent to the users. So from the charge, melting, casting, working, and then product. That's the flow sheet for manufacturing the product. Now let us see very simple, fundamental to understand why there should be different classification of stainless steels and so many number of types of stainless steels. Look at iron. Iron is a wonderful element. It has an ability to change its crystal structure as you heat it. You can see here this is the temperature and this is the 3 structures I put here. This phenomenon is called allotropy. Allotropy is the ability to change its structure as you heat the element. You can see here basically iron is available at room temperature up to 910 degree as alpha phase. That's the body center cubic as you see here the structure. Then you go to gamma phase from 910 to about 1390 or so. You have the gamma phase which is called a FCC structure, center cubic. This is called austenite and this is called ferrite. Now you go to temperature 1390 melting, you form a delta structure which is body center cubic, and this is called the ferrite structure. This is the structure with carbon. So if you are able to retain this structure, you have a ferrite structure. If you are able to retain this gamma structure, it is an austenite structure. Then this particularly this delta is formed during welding and other treatments. Now, depending on the structure, you have a classification of the stainless steels. Can be a ferritic stainless steel or austenitic stainless steel, and you also produce a modern stainless steel by transformation, faceless transformation. Now, I have given you a ternary picture of iron, chromium, and nickel. You can see here percentage of iron, percentage of nickel, and percentage of chromium. And if you look commercially, there are about 5 different types of stainless steels available in the market. The austenitic stainless steels, which are predominantly 65 to 70%. The ferritic stainless steels, 20 to 25%. The modern ferritic stainless steels, about 7%. Precipitation organic stainless steels, about 2%. And duplex stainless steels, about 1%. And if you take the number of types that are available, there are more than 150 numbers, types of stainless steels available. You can have an austenite structure by manipulating the chromium, nickel, and stabilizing the austenite phase, or you can have a ferrite structure by controlling the carbon and reducing nickel to 0 and having more chromium. It's a ferritic stainless steel. Or you can have a modern stainless steel to have a moderate chromium and no nickel and high carbon, so that you can play with this iron, chromium, and nickel, and you can try to have number of types of like 65 to 70% are austenitic type, ferritic are 20 to 25, and monostatic are about 7%. Now, typical, I have given the classification of ASTM. 300 series are austenite, and 400 series are ferrite. Some of them are monostatic. Duplex are in a different way it is designated. Precipitation hardening, and they have their advantages and disadvantages, and depending on their fabricability, their corrosion, their hardenability, their weldability, their mechanical property, and one has to make a choice of austenitic or ferritic or monostatic or duplex or precipitation hardening stainless steel based on the application that you are looking for. Now, coming to stainless steel, if you want to use stainless steel basically for any application, the following design parameters one should look into. In fact, I would recommend that any type of stainless steel you want to use for an application, the following parameters are very, very important. You can also refer to the ASTM standards, which will provide all this information. The alloying elements that are present, particularly the impurity elements in minor quantities, their role is very important. Grain size, how fine it is, how coarse it is. The thermomechanical treatment that it has undergone either during manufacturing or during fabrication, like percentage of cold work, type of cold work, the extent of cold work, the thermal treatment. Also the stability of service conditions. What are the temperature, load, the creep and fatigue conditions, creep fatigue interactions. The weldability, welding of these stainless steels are very important for making any component. Then the life assessment strategies. If you look at the alloying elements, you take the basic 304 stainless steel, which is very popularly known as 18-8, that is 18 chromium 8 nickel stainless steel, which contains between 0.06 to 0.1% carbon. One can play with this composition to get various types. For example, if you reduce the carbon to eliminate the problem of sensitization and intergranular corrosion, you get 304L stainless steel. If you add molybdenum to this, about 2.5%, it becomes 316 stainless steel, which has a lot of resistance for creep and pitching corrosion. If you add very high chromium and nickel, maybe 23% from 18 to 25% chromium and 20% nickel, 8 to 20%. Then it becomes 310 stainless steel for very high temperature applications with very good resistance for scaling. And then you can also reduce nickel and add manganese and nitrogen. It's, though there are, we also know about the two other series. I am here talking about 301 stainless steel, which is used for general applications. Maybe I will quote that for the metro rail today, the body of the cabins are all made of these 301 stainless. Then you have titanium and niobium to avoid the problem of sensitization and intergranular corrosion. Then it is called 321 stainless steel and 347 stainless steel. Then you have high molybdenum and nickel, the 904 stainless steel, which is also called Superaustenitic stainless steel, which has very high resistance for corrosion cracking and scaling. So one can manipulate with the composition to get various types of stainless steel, austenitic stainless steels. What are the applications typically? To look at the high temperature applications with required strength, probably from cryogenic to 1000 degrees Celsius, wide range of operating stress from 200 to 2000 megapascal, good corrosion and oxidation resistance from atmospheric to acidic conditions, then it is acceptable to multifaceted environment from food to aerospace. So it's a very versatile stainless steel, austenitic stainless steel. Based on the type of the stainless steel, you can use for various applications. Two important elements that I am touching here, the nitrogen and carbon, which are in steels and stainless steels. All of us know that both produce interstitial solid solution strengthening. Both form their compounds. But if you look at the difference is in the temperature. Easily beyond 450-500 degree, carbides will form if the carbon is more than 0.027%, that is 0.03%. Solubility limit is very low. Whereas nitrogen has very high solubility and the nitride formation is very sluggish and it occurs above 750 degrees Celsius. So nitrogen is having an edge here with respect to precipitation and also giving a much high temperature application. Both are improving the corrosion, strength and creep and fatigue life in limited quantities, but higher strength and ductility of nitrogen is seen compared to carbon in steels and stainless steels. I have some information which I can say that for every 0.01% of nitrogen that you add, you will get an increase of 52 megapascal in the yield strength for austenitic stainless steels. And both are economical. They produce large effects in small quantities. By increasing very small quantity, normally the carbon is limited to 0.03% to avoid sensitization in stainless steels. But nitrogen can be added as high as 0.4 or 0.5%. But one can very comfortably add up to 0.16% without any nitrate formation. And it is very economical. It is not an expensive element, and it can replace nickel, which is very, very costly. And commercial alloys with the different quantities of carbon and nitrogen are available in the market. The new class of nitrogenated materials are called high nitrogen steels and stainless steels. where intentionally large amount of nitrogen is added to achieve corrosion and mechanical properties. According to the literature, greater than 0.08% of nitrogen in monazite or greater than 0.4% nitrogen and above in austenitic matrix, they give wonderful change, improvement in the mechanical and corrosion properties. In the creep resistant steels, 0.1 mass%, and in the tool steels, 2 mass%, and in a normal steel, 0.9 mass% you can add to also get the benefit. In general, the high nitrogen steel or stainless steel, the high is referred to the condition where the nitrogen added in these quantities which give the desired properties. I also want to share with you an information that there is a high nitrogen steels and interstitial alloys, an international conference which will be held in this month now, end of this month, 27th to 29th September in Chennai at the Hotel GRT Grand, and it is organized by the Indian Institute of Metals Kalpakkam chapter and Ferrous and Metal Science Division of IIM, supported by the industries and the national agencies. Dr. Baldev Raj is the chairman, and Mr. Chetal is director of Indira Gandhi Centre, is the co-chairman, and myself is the convener. If you want more details about this material and if you are interested, you can refer to the website www.hns2012.com. Now, duplex stainless steels, coming from austenitic to duplex stainless steels, they have a mixed microstructure. Austenitic stainless steels are gamma phase FCC structure, whereas duplex stainless steels are mixture of austenite and ferrite, 50-50. They provide significantly greater strength than austenitic grades and exhibit good ductility and toughness. There are family of grades having good corrosion resistance, high strength and ease of fabrication. And these duplex stainless steels, if you look at this PRN, that is called pitting resistance equivalent number, pitting resistance equivalent number, which is percentage of chromium and 3.3% of molybdenum, 0.5% of tungsten and 16% of nitrogen. These are the major elements. Generally, PRN is greater than 32 or so when it comes into duplex stainless steel category, and they have very great resistance to stress corrosion cracking and corrosion fatigue compared to 300 series of stainless steels. And in this case, a very high nitrogen is added in duplex, which increases heat effective zone toughness, corrosion resistance in these alloys. They also inhibit intermetallic phase precipitation. If you look at this duplex, they are neither austenite nor ferrite, and they are in between. These are the, you can see here, then the border of austenite and ferrite, 50-50 duplex classes. And there are a number of types of duplex, which is the leading duplex SS is 2304, which is a very simple one. Then the standard duplex is 2205 variety, which is nearly 80% of the duplex are available in this category and which are being extensively used in the industry. And then you have a super duplex where the pitting resistance equivalent number is about 40 to 45. In this case, very high chromium, 50% increased molybdenum nitrogen is available in the 2507 category. Then today we also have hyper duplex, which are much even higher than pitting resistance equivalent, higher than 45, and which is also used for very specific applications. The beauty of the duplex stainless steel is that it is basically from a primary ferrite solid case. It goes through a ferrite austenite zone where it gets appropriately separated 50% ferrite and 50% austenite below 1000 degree when it is being cooled. And if you want to get this 50-50, you have to control this chromium equivalent and the nickel equivalent following this percentage ferrite so that you will get only 50%. It's typically a kind of a microstructure where ferrite is available as a darker phase here, and the lighter one is the austenitic matrix. This is the lighter one. Look at the typical composition here. You will always have very high chromium. You can the lowest is about 21 to 24. You will have very high chromium and less nickel, and molybdenum is also high here. Nitrogen is added, you can see minimum 0.1 to up to 0.6% is added here. In some cases, copper is also added. And specifically the 2507, the super duplex has got tungsten also. On all this additional tungsten, copper, high nitrogen along with very high chromium, provide excellent corrosion resistance. But one of the problem of using duplex stainless steel is its tendency to form some embrittling carbide, carbonitride, and sigma phases, and then these kind of phases affect their toughness and strength. And particularly because this the ferrite phase has a tendency to undergo 475-degree embrittlement, and the precipitation, the spinodal decomposition of the alpha pi microstructure that is present to produce this such intermetallics like sigma, chi, and also some nitrides and carbides even at lower temperature will lead to a problem. And when you have the copper added alloy, this can also form an epsilon copper precipitate, and otherwise because of high nitrogen you will have chromium nitride precipitates, and all these precipitates which are formed will lead to some kind of problem with respect to their embrittling behavior. So you have to be very cautious when you are using for temperatures beyond 475 degrees Celsius. And if you compare otherwise, if you use it as a wrought alloy, you see austenitic, ferritic, duplex, molten static, and precipitation. With respect to all these properties, strength, wear resistance, permeability, workability, resistance to general corrosion, resistance to picking corrosion, resistance to stress corrosion cracking, you can see that compared to austenitic, ferritic, molten static, and precipitation hardening, duplex is meeting almost all the requirements. It is one of the best choice. And that's how it is being used in oil and gas industries, and also used for various other applications, particularly pollution control equipment, where very severe environment consisting of even higher than 30,000 ppm chloride. I'm sorry, it is ppm chlorides, even up to temperature of 55 degrees Celsius and pH 6. And also used in the building and construction, the rebars, or it can be used also for design and construction of the decks and bridge component parts. Pulp and paper industry is the most benefited one. All the digester, pulp storage tanks, drums, bleaching equipments where a very high chloride and sulfate combination is there. And lean duplex, the most common one is used for liquid tanks and suction roll in the paper mill. And urea plants use specific grades of duplex for the urea carbamide stripper and condenser. And most of the chemical processing, transport, and storage were not high temperature, and most welding are not used. Mostly duplex are used as pipes and tubes and so on, because there is not much welding and high temperature is involved. The superaustenitic stainless steels are those containing more than 50% of non-ferrous elements, like the chromium, nickel, and molybdenum. If you add, that is more than 50%. The rest is only iron. And they have the same structure of the austenitic stainless steels, but as I told, they have very high chromium, nickel, molybdenum, copper, nitrogen, and so on. The most common types of them are the AL6XN, 9R4L, 25-4SMO, 25-6SMO, and 1925HMO. You can see their composition here. The nickel is very high, chromium is also very high, molybdenum is there at nearly 5-6% up to that maximum. And the copper is there in some alloys, and also nitrogen. And this combination of very high alloying elements make them super austenitic. That means a very stable and highly corrosion resistant variety for selective applications. And it has a typical austenitic structure, but they also have some kind of banding, compositional banding, where the partitioning of chromium and molybdenum takes place, and they have, because of the high chromium and other alloying elements, it forms a tendency to form the sigma phase. And you can see an austenite boundary with a decorated sigma here, courtesy to the website. You will find in the internet this kind of works reported. It has very good application. The corrosive, including corrosive food and beverage products are there, are chemical, cosmetic, brewery, desalination, semiconductor, aerospace, bioform, pulp and paper, and gas handling applications. But you must remember, as the higher alloying elements are there with chromium, nickel, molybdenum, copper, and nitrogen, the cost is also many times higher than a typical austenitic stainless steel. And it is rightly chosen for breakage water, seawater, pulp mill, bleach plants, and other high chloride process streams. It is definitely a cost-based, cost-effective, cost-efficient alternative to nickel-based alloys and titanium, because they are much superior in cost compared to the inconel and the Hest alloys and Heinz alloys, many other varieties. The superaustenitic stainless steels are economical replacements. You can see I have also put the typical applications, including flue gas desulfurization, oil and gas production, and for various chemicals at very high halide levels, food processing, solvent distillation columns, pulp and paper bleach, and seawater handling. Now we have seen all this austenitic, duplex, and superaustenitic. One important factor is that, as I told, why this stainless behavior? Because of the chromium oxide film that is present whenever the chromium content is beyond 10.5% in the steel. And that is how that we get this thin adherent self-healing chromium oxide film, which provides the protection, but they are attacked by halide ions. Halide ions means a group of ions like chloride, bromide, fluoride, and iodide. And these ions, they come to the surface, they make attack at selective places where the passive film is weak, and then they make corrosion attack selectively at these places, forming some cavities like this, which are called the pits or pitting attack. And this localized damage can lead to not only pitting, but also to crevice corrosion, intergranular corrosion, stress corrosion cracking, corrosion fatigue, etc. So the application of stainless steel, whatever may be the type, when it is used for an industrial condition, they all undergo this localized corrosion damage due to the specifically attacked by the halide ions like bromides, fluorides, and iodides. In general, we have seen what is corrosion, but corrosion is not a single phenomenon. It's like we have some disease in our body. We are not well, not because of a particular disease. There can be different types of diseases. So the materials also have corrosion, which is a disease, in different forms. Their corrosion manifests in different forms. Uniform corrosion, pitting corrosion, crevice corrosion, intergranular corrosion, stress corrosion cracking, threatening corrosion, hydrogen embrittlement, corrosion fatigue, erosion corrosion, galvanic corrosion, high temperature corrosion, microbially influenced corrosion. All these happen on the surface of material, and I have given a typical schematic picture of various types of corrosion. And all this happen because of the heterogeneities that are present on the surface. Every metal and alloy will have some heterogeneities starting from their grain boundaries, the secondary precipitates, the casting defects, the weld defects, and also some stresses that are present, or some precipitates, inclusions, whatever that is heterogeneity present on the surface will always provide site for the corrosion to start from the surface. I want to give a few important corrosion types of stainless steels. The most important is the pitting corrosion, formation of a cavity or the hole on the surface, which can be a narrow and deep, which can be elliptical, which can be wide and shallow, which can be a subsurface attack. The top surface, you will never have a feeling of corrosion attack, but it may be a very bulky one at the bottom. And the undercutting, horizontal and vertical, most of these pits are in sizes of micrometer and below, that you will never know that it grows at the bottom of the metal surface into a very huge cavity, but on the top you will see only a micrometer attack. And when it goes beyond the required depth, then it gives the site for the corrosion cracks to start due to fatigue or due to fracture, mechanical fracture. And this typically occurs when there is an anodic dissolution selectively due to the halide ions, as I told you in the place. And since it is small anode and there is a large cathode, and it is also accelerated in nature, and there is an autocatalytic mechanism that once chloride enters this pit site and the pit is growing and it continues to grow, and you will never be able to stop, because the chloride that is getting collected in this pit will give always the possibility for the pit to grow. So there are methods by modifying the alloying elements, add certain elements like molybdenum, nitrogen and nickel, which will slow down the pit growth. Or you can have some protective coatings on the surface which will avoid the pit to start, or you can add inhibitors to the medium that will avoid the pitting, the chlorides and other pitting agents to attack. I am giving you a small example of 304L stainless steel cryogenic condenser, which is used for cooling brine. It is used to cool acetone vapor mixed with methanol, and which is cooled by a brine, and this is made of 304 stainless steel. And over the period, within a short time of about 3 months, there was a leaking attack at the coils. You can see the pits that are formed and that made to leaking. And the investigation mentioned found that when you have only chloride, such pitting attack will be very significant. And the study showed that there was sometime ordinary water was used to prepare the chemicals, and this ordinary water contained more chloride, that has led to the pitting. Instead of TM water, which was not available for a short time, ordinary water was used, and that contained a large amount of chloride ion that led to the pitting attack. Intergranular corrosion is another important type of corrosion of austenitic stainless steel, which happens in a sensitized structure. You see the grain boundary is selectively attacked, particularly in a welded component. In the heat affected zone very close to the weld area, the corrosion attack is due to the sensitization. What is sensitization? During heating and cooling, normally stainless steel, which contains 18% chromium, forms some chromides, chromium carbides along the grain boundary, which contain about 65% chromium. So the region which is very close to this grain boundary gets depleted in chromium less than 9%. That means it takes away the passive film nature of the interface between the matrix and the carbide, which is very, very small in this line. So selective attack along this grain boundary takes place, that is leading to the intergranular corrosion. This phenomenon of forming a chromium depleted zone due to the chromium carbide formation, whenever stainless steels are heated between the temperature range of 400 to 750, is called sensitization. Always any sensitized microstructure will undergo selective localized corrosion like pitting or intergranular corrosion, and this is unavoidable in service whenever you are using austenitic stainless steels. This can happen either due to isothermal exposure, due to the service temperature or stress relieving heat treatment, or due to continuous cooling, either during hot working or welding operation or stress relieving heat treatment. And this heating and cooling between the 400 to 750 is unavoidable during this kind of isothermal exposure and continuous cooling. And how to avoid this sensitization? You reduce the carbon content, because carbon forming carbide is the root cause of this problem. So reduce the carbon less than 0.03%, and you can avoid carbide, you can avoid the formation of chromium depleted zone. Or you can add titanium and niobium added stainless steels, which are called 347 and 321, which will stabilize the titanium and niobium carbide and will not allow the chromium carbide to form and the subsequent chromium depleted zone. Another option is that you have done the welding, you have done the heat treatment, you are having an apprehension that the chromium carbide would have formed and sensitized structure is there. Then you can heat it to higher temperature, around 10,050 to 1100 degree, and water quench rapidly. Then you will find that the carbides are redissolved as carbon and chromium, and you avoid sensitization. Additionally, one of the options is add nitrogen the formation of carbide, and it will not be creating a sensitization problem. Nitrogen up to 0.16%. Crevice corrosion is whenever there is a metal to metal joint, the joint place is metal to metal or metal to non-metal, the joint is undergoing selective corrosion attack. It happens due to the chloride level, and this is mainly because there is a selective depletion of oxygen here, and also the concentration of the chloride is different here. Chloride diffuses, and selective corrosion takes place between a metal and non-metal, like a gasket or a metal and another metal. So where there is a restriction of space, say in micrometer square area, where diffusion of ionic species is not possible, concentration of the ions like chloride or depletion of oxygen leads to crevice corrosion. And I will tell you, it may appear like a very small type of corrosion, but you see such a huge heat exchanger used for a carbamate heat exchanger in a fertilizer industry. The tube to tube seat of this joint had some poor tube to tube expansion, and there was a gap here of few micron. The gap, and then it has led to severe corrosion, and you can see that there was a leaking, and within a short period of this brand new heat exchanger, which was imported, got into a problem mainly because of the crevice corrosion that took place between the tube and tube seat. Stress corrosion cracking is another major type of corrosion, which is mainly due to the combination of the tensile stress and the particular specific environment. It is a combination of a tensile stress under specific environment, like material like stainless steel, which is susceptible to stress corrosion, and it undergoes to stress corrosion cracking. And there are different combinations like high strength steel, you have hydrogen and hydrogen sulfide; mild steel, you have hydroxide, nitrate and carbonate; and austenitic stainless steel, you have chloride, hydroxide and high temperature water. This is a typical example of a storage tank for helium gas made of 304 stainless steel. You see where there is a weld seam here, and after the weld it was undergone hydro test to see the leak proof, and then the workers left with some water which was not drained completely after the hydro test. Unfortunately, they used normal water and not DM water, and that contained a lot of chloride. Because of this weld, which is not undergone any stress relieving, the residual stress produced after welding, plus the chloride that was present in the water that was left out after the hydro test, led to the stress corrosion cracking. So this is a very important type of corrosion that happens, and the entire tank has to be discarded. Microbiological corrosion is one of the most important corrosion. Today it is felt by the industry. All the aquatic environments will have these microorganisms and macroorganisms, and they have a tendency to attach on any metal surface to get the nutrients. And then they release their excretion that forms exopolymer, which attracts further microorganisms. They form a colony or a biofilm, and finally it becomes a deposit meshy product, leading to corrosion under that. There are also certain type of bacteria that can eat the metal by reducing the sulfate that is produced. That's called sulfate reducing bacteria, and all these type of attacks due to micro and macroorganisms lead to it's a common problem in the industrial process due to the presence of all these in the aquatic environment and the nutrients that are present on the metal surfaces. Now coming to the surface finish aspect, normally a smooth and fine surface or an electropolished surface is very good for avoiding corrosion problem, while a rougher and a coarser surface will attract the condensation of moisture, and then the surface attack will be more in the case. So better surface finish, finer surface finish is good for having better corrosion resistance in service. If you want to handle and properly use the stainless steels, you have to be careful of these following points. You have to avoid embedding surfaces with carbon steel. Normally people manufacture stainless steel component in a workshop where carbon steel is also fabricated, and they don't realize this. Carbon steel is a very hard component which will get embedded on the soft matrix of stainless steel, and it will cause local rust spots, and scrapping with steel tools or surface also make such things. Grinding debris attached to the surface, and we have to remove this by pickling treatment. And this is very important, and after that you have to also test for this removal of iron by peroxide test, or you have to also ensure that with pickling and passivation such things are removed. And sometimes even the heat sink that is present after welding also should be removed by pickling, and the surface contaminants like slag, dirt and paint, some chalk marks, pencil marks, all that should be removed when you are handling finished stainless steel component for any applications. And pickling, passivation is well known to all of you that pickling is a descaling process using a chemical like acids, and passivation is again a treatment to form an artificially an oxide film on the surface. Particularly it is done with a mild oxygen like 10 or 20% nitric acid. There is an ASTM process, and this never end with only pickling. You should always follow with passivation. And every component, when it arrives to your industry, you have to ensure with your fabricator that the final step should be pickling and passivation. Or before you put the component into the final use, you must ensure that they are always pickled and passivated. Welding is another important problem. It is an indispensable tool. Without joining, you cannot make a component. And for TIG welding is commonly used. If you take a typical, I can tell you some typical boiler that is made of a stainless steel or a kind of a nuclear reactor primary vessel, there will be tens of thousands of weld joints which are made of TIG welding. Because welding is done in an open atmosphere, though it is shielded with argon, the weld torch is shielded with argon, the melting and then cooling under a condition which is not controlled will lead to heterogeneities in the structure. There will be a heat affected zone due to the thermal cycling by multi-pass welding. Also the weld structure will be very composite in nature. There are two issues with respect to austenitic stainless steel welding. One is hot cracking due to the impurity elements that are present, or the other one is the sensitization in the heat separator zone, which we have already discussed. So one has to take a lot of care to avoid these two issues: hot cracking by controlling the heat input, or by controlling the chemical composition of the base as well as the pillar wire or the welding electrode, and sensitization also by controlling the other parameters. But whatever it may be, many times, as I told in the beginning, people think that stainless steel is something a divine material. I can do anything with that. But there are many misuse and abuse of stainless steel. You can see that nuts, bolts, and blinds and flanges, etc., are newly fabricated newly fabricated stainless steel stains. Generally, people left open in an atmosphere without much preservation. But they think that stainless steel can be easily withstand the corrosion and it can work even without any preservation. Storing of stainless steel component along with rusted and used carbon steel in equipment storage yard, which is very commonly seen in any industry. You should not do that. You have to separate them. Stacking stainless steel pipelines along with carbon steel, that is also a very dangerous one. Improper insulation and not closing after subsequent repairs and inspection, that is also very important. If you have an insulated component used for high temperature or any other application, whenever you do some repair or inspection, you should close it properly so that that place is not vulnerable for the chloride or any other aggressive ion to enter and then start the localized corrosion. Improper fitting of galvanized iron and MS nuts and bolts and flanges with stainless steel providing galvanic effect. This is also, people think that for strength point of view or economic point of view, people use galvanized iron or mild steel nuts and bolts for a stainless steel pipeline. That's very, very dangerous. This is mainly because technical knowledge is not there, and it is necessary to avoid such kind of misuse and abuse of stainless steel in industry. I give an example of a stainless steel component that is kept under storage for over 20 years because the management wanted to keep them for further use as a replacement or an emergency requirement in a plant, but the plant was in a coastal atmosphere and salt condensation was regularly happening. Though it is a structure where it was kept, but it was not preserved at all. So when we opened up and then we are trying to see the purpose of this storage place with respect to stainless steel component, what you will be surprised, and it's amazing to see the pipes are with the stress corrosion track, and you can see the straight T and eccentric reducer and the weld neck flange. They are all rusted. No one believes that it is stainless steel. It is almost like alloy steel or steel. That is mainly because they were never preserved. Prolonged storage with less inspection and maintenance resulted in rusting of stainless steel. It's very, very unusual. Chloride content in coastal atmosphere is very high. Condensation of such chloride over stainless steel surface with dirt lead to rusting and localized corrosion. Deficiency in storage, unsafe staking, mixing of steel and stainless steel component, poor humidity, air circulation, temperature and cleanliness are the root cause of the failure. Absence of surface treatment of the finished component. You can see some of the surface components after they are finished, they were not pickled or passivated, they were as fabricated condition they were kept. That was one of the reasons. And pipes were stored without any plastic insert. Normally the pipes, both ends should be closed with a plastic insert so that moisture doesn't go there and condense, or rainwater or anything that does not enter and starting corrosion problem. The main problem was fitting and stress corrosion, which was mainly due to poor storage conditions. How do you then avoid? Please take care residual stresses introduced during fabrication and sensitization occurred with high heat input welding are relieved and annealed prior to storing. This is very important. If you want to identify, scribing is preferred in place of engraving. Water shall be completely drained after hydro test. Contact of finished parts shall be made using hand gloves only if it is a very finely finished or pharmaceutical, food, beverage and maybe nuclear applications. Always pickle and passivate fabricated parts prior to storing or prior to commissioning. Check for corrosion damage by dye penetrant test. If it is stored for a longer time, you should check for the corrosion attack. You have to use DM water for all this purpose with less than 50 ppm chloride for dye penetrant hydro test and for preparing, degreasing, pickling and passivating solutions. Store SS spots separately. Iron contaminated stainless steel shall be avoided. Storage area should be maintained. Check for quality of sealing once in 6 months. But still, I find a lot of inadequate and improper poor maintenance has led to a lot of corrosion, and which is the cancer of your machine. And this is what is a major problem that we see in industry. that poor knowledge and poor awareness of using that. There are a lot of precautions I am listing out. You can go through leisurely, but I will simply quickly run through because we are running short of time now. During transport, all sheets and pipes needs to be wrapped in polythene sheets along with silica gel. And when stacking for easy handling, you should have plastic pipes should be separated by wooden or so. And this should avoid normally observed deep scratch marks. Ensure that all specifications are adhered at the time of acceptance of the material. Plasma cutting. After plasma cutting, heat application zones should be grounded or machined to remove unwanted microstructure. Shear cutting of solution in plates will introduce residual stresses. Such plates should be protected during long storage. Fabrication such as drawing, stretching, rolling, bending, shearing, etc. will introduce residual stresses. These should be kept to a minimum. Force pits during welding shall be avoided. Weld spatter and fumes from coated electrodes can leave fluorides or chlorides should be avoided. Dark heat tint which is present on the welded surface is an unprotective offset film. This should be removed by pickling and passivation. Including the bird droppings and lubricant oils should be cleaned with DM water. Even human sweat contains chloride, so I recommend to use gloves instead of using naked hand to deal with finished components. Pickling and passivation is a must after passivation, and you have to ensure that scales are removed. Finally, the components should be dried up totally. Stamping should be done should not be encouraged by any stamping process. It should engraving is better. It will introduce a lot of local residual stresses. I give you a lot of references. This you can go through. These are wonderful sites where you will give additional reading to enhance your knowledge. I try my best in this 1 hour to give whatever information that can give an eye opener for you about stainless steels for corrosion prevention. And I am sure that by going through that, you will be able to enhance your knowledge and come back to me or to CII for getting additional knowledge. Thank you very much. I want to finish my talk by saying that rust never rests, and rust can put your business into dust unless you take care of them. And thank you very much for all of you to be with me. And I am requesting you to one by one give your questions. And I think I am given 30 minutes. Those who are not able to give me the questions can send the email and also call me for any clarification. Thank you. Thank you very much. My request is that if you have any of your own problem in your application or in the industry, kindly send detailed information by email to CII or to me, because it may take longer time to understand, and we will need definitely additional information to make a judgment or decision. And that's what is my suggestion. Yes, there is a question from Varghese K. Jacob. We have got a calcine cooler, the purpose of which is to cool the powder calcine from 950 to 250 degrees Celsius. At present, we are using ASTM SA5115 grade carbon steel material in the heat exchanger portion. I think it's a very long question, Mr. Varghese. I will highly appreciate if you can send me a email to CII or myself. We can address this, and definitely we will try to help our best. Okay, the life of the cooler, you say 1 year. And stainless steel you want to, because you have to tell me also what are all the total process from starting chemical to final. You are doing calcination process at high temperature. And the simple solution I will tell, if you are trying to use, it must be 310 stainless steel. But you want to do from 950 to 250. 950 is the upper limit of austenitic stainless steels. Offhand I can tell 310 stainless steel, but I will need much additional presentation. Additional information to answer you. And CII has promised that they will put in my CII the presentation later also. Yeah, 431 used in pump application, Mr. Ravi. It has good corrosion resistance. Moreover, it also has erosion resistance. I hope what environment that is being used. I am not getting it. Pump is used for either seawater or for any acid or any what is the application is missing. See, 304 tanks in open area, just now I have mentioned, Mr. Ashok Prabhu, see, it has to be fully dried up, cleaned. First you clean it, dry it up, and then cover it with some plastic sheets with some silica gels and other preservatives. That is very important. It should be kept in a closed place also. And if you are going to keep it for longer time, you should keep checking them once in 6 months at least to see the condition is fine or not. And keeping it in the open area is not at all recommended. Cost of SS2M sheet, it's Mr. Pramod Sharma, you can go to a vendor or in the market. Stainless steels are available. Basic cost of, say, you can get Chinese varieties from rupees 100 a kg, 100 rupees per kg to you can go up to 1000 rupees for a better quality. And I don't know what type of stainless steel you want and how much area, how much quantity you want also. You please contact a vendor. That is very important. The hardness of cooling water in high temperature heat exchanger is very, very important. There is a limit, but offhand I will not be able to tell you now. You have to also have the Langmuir index, which will tell about the hardness of the water and the scale thickness. And if you can send me a mail, I will provide you the information. How to find out the food grade steels presently using hardened SS410 in mixer grinder spindle. I think mixer grinder spindle you may need it for two purposes. One is for corrosion and another one is for the hardening, because it has to also use for a grinding application. 410 is a very good material for such application. If you have any issue of corrosion, because either you are not given again the medium where you are using, that is very important. Mr. Manoj Kumar. 431 and 430, yeah, 431 is also a good variety. 430 instead of 410, you can use 431. And since it is not going to see temperature beyond, it's a ferritic grade, you can use 431, which has much better alloying elements for good properties. The ASTM A381, which gives you the pickling and passivation method after fabrication, ASTM A380 and 81, you can contact any ASTM procedure, you can get it, Mr. Ashok Prabhu. While doing pneumatic test, what care should be taken in SS vessel? If you are doing pneumatic test with air, it's not a problem, but if you are going to do with hydro test, then only you should be worried about the quality of the water that is being used. But still, if you are doing pneumatic for a very strategic or a very sensitive stainless steel component, then you take care that the air does not contain much of moisture which will get entrapped or which will get condensed inside. Use of 321 grade for fume exhaust fan impeller. Earlier we are using chloride. Is it okay? For chloride, 321 is good. It's a good variety only for exhaust fan impeller. I want to join two SS parts using GI studs. Whether corrosion is occurred, definitely it will occur. You should not use GI studs. Maybe you can use a chromium plated GI stud. That also you have to ensure that at the joining point that the coating is not removed. Better to use stainless steel with stainless steel nuts and bolts. That will give a longer life, Mr. Johnson. Can we have cost comparison between duplex compared to 304? It will be definitely maybe about from 5 to 10 times, depending on the 304. 304 you can get a standard variety for about, let me say, simple 150 to 200 rupees, good quality, but duplex will be around 300. So 300 to 500, a normal lean variety. So that is the cost difference you can feel. You can contact CII, Mr. Krishna Rao, to get the PPT of this. Can we use 304 SS in coastal climate at seashore, please? Yes, you can use, but you have to periodically preserve and maintain. As I told that the salt layer should not be present on the surface for longer time. So it will lead to chloride pitting. So you have to maintain the 304 for very carefully when you are using in seashore and coastal surface. AOD process is equivalent solution. No, AOD is a argon oxygen decarborization process which is normally used for producing stainless steel. See, after melting in the electric arc furnace, the melt is taken to AOD process where carbon as excess carbon is removed by argon oxygen decarborization. Solution annealing is different. Solution annealing is when a wrought alloy is prepared, if it has some carbides, if it has some other unwanted precipitates, to dissolve them into the matrix, you take the wrought product to higher temperature, maybe 1050 to 1100 degree, and cool it rapidly such that all these elements are in the matrix. They are not available as a precipitate or carbide. Dye penetrant test, will it show the corrosion damage that has already happened and it is severity? Whether can this test be done? Can corrosion be predicted? If so, for what working life? Mr. Manoj Kumar, see, it's a very good idea to use dye penetrant if you suspect some corrosion attack on the surface. It will tell you the location. To some extent, it will tell you the extent of corrosion. But you have to further do some ultrasonic or eddy current or any other test to see the real percentage of the attack. Dye penetrant will give qualitatively information. It will not give you a quantitative information of how much depth. All this valuable information is very difficult. Mr. Ashok Prabhu, how inhibitor addition is done to corrosive medium? It depends. See, I don't know what is your medium. If there is a possibility, you can add some like organic inhibitors, which will not affect your process, efficiency. In small quantity, you can add this kind of organic chemicals, which will complex all these other damaging ions like chloride ions and help you. But you have to think carefully whether that will affect your process. For SS 431 round rods, what should be the supply condition to meet good corrosion properties? I think I recommend you to go through the ASTM standard, which gives, because depending on your finish application, the surface finish or surface condition is always recommended for your purpose. Alternate cost-effective material for mixie spindle working high RPM. Percentage of nickel reduces, cost will be reduced. Please advise. It depends what, if it is a lower variety, you can go 400 series where you will get adequate wear and corrosion resistance. If you are going for very high end of your mixie, that means costly mixes, you can have a nickel-based alloys or high nickel superaustenitic or austenitic stainless steel, which will also give very good performance, but the cost will also increase accordingly. My email ID is in the first slide, please. You can use that. For corrosion protection on MS roller, what process is best for long protection? Hard chrome, nickel plating, zinc plating. See, MS roller, I don't know what for is the application. If it is going to be an expensive application, I recommend hard chrome. For example, if it is a textile mill roller or if it is for some paper mill roller, better you go for hard chromium, which is better, or nickel plating, not zinc plating. But you have not specified what application where it is used. Mr. Achaya. 431 will not fully qualify. It may. I have not done this testing and I am not aware of this. Mr. Ravi, you can always refer to the literature and find out. I am sorry, I don't have an answer for this question. 431 SS will qualify for salt-free test. Please check. Is there any special welding medium to be used for special stainless steel materials? Nothing like a welding medium, Mr. Mohammed. Thick welding is the process. Normal gas tungsten arc welding, and you can use with filler wire, and you can also use, if it is a thick component, shielded metal arc or the MIG welding. And the medium means, welding medium means, it's only always an argon protective shielding is required, because otherwise the weld during welding the melt will interact with the atmosphere. In cryogenic vessel, how to ensure the corrosion resistance of the outer surface of the inner vessel, which is insulated. perlite powder from the jacket vessel, carbon steel. Very difficult, very difficult. I am not able to visualize your application and component. If you can send me more information with sketches or something, then I can try my best, Mr. Manoj. Yeah, for textile, food and beverage, so you go for, definitely you should go for hard chromium plating, or nowadays even this heavy, high velocity oxyfuel, HPOF arc melting is there. You can do chromium melting and you can do nickel melting. You also have so many other melting available which will give very high hardness, good corrosion resistance, and there are some companies in India, they are doing also. Particularly for textile, food and beverage. If you want to give a MS roller, you want to give hardness, hard coating, like instead of chromium plating and nickel plating, you can go for spray, that is better, thermal spray processes. For handling liquid nitrogen gas at minus 196 degrees Celsius, we are going to use SS 304 pipe, which is the best grade to cryogenic temperature. You can use 304 pipe, it is very good. And it will work very well for cryogenic application. That should not be a problem. Your presentation material, Ms. Manoj Kumar, you please write to CII. They will send you. For SS 431 round rods, does sulfur has any impact on corrosion property? Yes, yes. Any steel and stainless steel, if you have more sulfur, sulfur is of course required if you have welding applications, because sulfur will help in the arc melting and convection. It will help, and it will help also in the machining. For better machining, but if you have very high sulfur, then you will have inclusions forming, and that will affect corrosion. Corrosion will selectively take place on the sulfur, which will be present as sulfide inclusions. What SS material is suitable for using with ozone? 68% Venkateswaran. You can use 304 SS. Typical 304 SS is good for you. We are presently using SS 304 for pressure cooker. Can you please advise any other equivalent material for its? If you are looking for very high strength and it's going to be used at high temperature, high pressure, and you will have all kind of food inside, creating acidic conditions or salty conditions, you can go very high end of material. If the customer is not bothered about the cost, you can even use Superaustenitic stainless steel. You can give the duplex stainless steels, and here the application has to be thought with respect to the cost. Otherwise, a normal 304 stainless steel is good for you. What action can reduce the rusting tendency once corrosion has commenced? What are the normal methods of rust removal? Moment you see rust on stainless steel, the first thing you have to do is that you have to do kind of first wherever the rust part is there, if it is of a very thin, small in magnitude, you can just even grind it off. If it has only, if it is appearing only for about say 0.1 millimeter, and if the component is 6 millimeter thickness, and if this is 0.1 millimeter, you can just grind it off. Very simple thing people do in industry for the components. But if the component thickness itself is 1 millimeter thick, and you have 0.1 millimeter, very difficult. In that case, wherever your component is rusting, you have to remove mechanically by any method all the rusted spots on the surface. Then you do pickling and passivation and reuse it. It will extend your life tremendously. It will extend the life of the component tremendously. Nothing will happen if you store ferritic steel and austenitic steel in the same place, provided they are separated by stacking. So you have to either cover with polythene sheet separately you store, or you have some wooden stacking that will separate them. They should not be in contact. If for a longer period, if you are keeping them together, it will undergo galvanic effect. If you are using already MS rollers with chromium plating, zinc plating, if you are not able to control the corrosion means, my first guess is that the quality of the plating is poor. They are already having some defects like pits, crevices and fissures through which your corrosive medium is entering. I think the quality of the plating is poor. Number two, if you are going to do, don't worry about the cost, you go for spraying, thermal spraying of chromium or chromium nickel alloy. That is much better. Or even zinc you can do by spraying, thermal spraying, which will give a very hard and diffuse surface. SS431, yes, you can do pickling and passivation. It will have different composition of the acid. Finally, you have to do. Before your final application, you should do that. In stainless lid, we made etching process to improve aesthetic. It became corrosion on that etching area. Any other solution? So Manoj Kumar, it is because of the type of chemical that you have used for etching. And then I will tell you, wherever you are etching, that place is attracting the corrosive chemicals there, like the chloride ions or anything, any chemical that is being used on that etched area. So after etching, that area has to be, you have to give some kind of treatment which will not expose the etched area for corrosion. And I do not know how you are doing this etching. No, you cannot use brass or copper bristled brush for stainless steel, like carbon steel and bristled brushes. You can use SS bristled brush. It is available. That is much better. So am I close to the question and answer, my dear friends? So let me thank you all for attending this lecture and putting all your doubts. I would recommend that you please send if there are any further questions, if there are any further kind of clarification, please send to CII. They will compile all the questions and send me, and it will be easy for me to give my ideas and suggestions in one stage. Rather than everybody send me, then my mailbox will be full with a lot of questions. I will be thankful to you if you send to CII. And if anybody wants presentation material, you can always approach CII. They will be able to tell you more information. And I have given, please see in one of the slide end, I have given the references that are suggested. Okay. So I will say that if you can see the references, that whatever I have mentioned in the end, you can also use some of the websites that I am showing. The last but one, no? You can move continuously, yeah. Putting F5. No, it will go to the customer. Leave it. Yeah, you can see here I have given handbook of stainless steels, ASTM standards. I have given a lot of websites. You see some of the stainless online. You can ask questions there. Nickel Institute site website is there. World Stainless Organization I have given. Then Australian Society of Stainless Steel I have given. British Stainless Steel Society I have given. And also Wikipedia and free encyclopedia also you can go. All your questions, there are some online. You can become a member, free membership is there. You can get a lot of questions there. Okay. And all this will be possible. And if you have any stain formed during pickling, that means your pickling chemical composition is very strong or it is not properly made. You have to be careful in choosing that. That is one important point. And I will recommend that please don't end with this lecture. You go to all these internet searches. You will have, all of you will have a laptop with internet connection. You can put your questions there also. You will find much simpler version of the information whatever I have given in this lecture, which will be useful to you. There are some videos available. You can get educated more, and please improve your knowledge, because never think that stainless steel is a divine material and you can do anything with that. And it is a myth that stainless steel will not corrode. It will also corrode, it will undergo a lot of problems. I know all of your practical people you are facing, that's why you are attending to know more knowledge on this. Thank you very much for joining with me. Thanks to CII. Thank you.
Well, ladies and gentlemen, Dr. Mohandas from CII Chennai. It's really a pleasure that Dr. Mudali came here all the way, very far from this place, and from there he had come here to give the talk. And the way he answered the question, as the question was flashing, immediately he took on and answered. It shows the depth of the knowledge that he has and the knowledge that he would like to share with all of us. Really a pleasure, very nice of you, Dr. Mudali, and we are very well benefited. Just for the information of all the participants, ladies and gentlemen, entire thing will be available on the CII website shortly in a couple of days' time. All that you do is click and see the whole thing. As he has already mentioned to you that the presentation will be available, and since it is, instead of only a presentation part of it, since it is a live one, you can see him presenting it, and each slide, what he is explaining also you can see it in that. Apart from that, the references that he has mentioned, you will be able to see it in that slide, and you will be able to get on to all those sites. Once again, on all your behalf, on behalf of CII, let me thank Dr. Mudali to have come here and given us this. Thank you very much.
Thank you. Thank you very much.